Hello, everyone. Hope all of you are fine. Today, we are taking a new topic in quantum mechanics. That is the three-dimensional case. In that, we are going to obtain three-dimensional Schrodinger equation. And then we are going to see that how the three-dimensional Schrodinger equation can be used for solving different problems. Now, before coming to that, let me try to share the PowerPoint presentation. So in sharing the PowerPoint presentation, we come to the slide in which the title is the three-dimensional Schrodinger equation. So three-dimensional Schrodinger equation we are going to discuss today. So three-dimensional problem, Schrodinger equation. And in that, let me share the first slide, the Schrodinger equation in three dimensions. Schrodinger equation in three dimensions in Cartesian coordinates is written very simply, and that is shown by equation number 1, where minus h cut square divided by 2m del square plus Vr psi r equal to E psi r. And we know that del square is d del 2 by del x square, del 2 by del y square, and del 2 by del z square. That is equation number 2. But in the polar coordinate system, that is r theta phi coordinate system, operator del square is written in a complicated manner. And this is done in a mathematical physics books. So we don't want to spend time how operator del square is obtained in polar coordinate system. But we write in a ready-made manner. But we can refer mathematics books or mathematical physics books how the derivation is done. So operator del square is written as 1 upon r square del by del r square del by del r plus 1 upon r square sine theta del by del theta sine theta del by del theta plus last term 1 upon r square sine square theta del 2 by del phi square. Now, this is named as equation number 3. Schrodinger equation in polar coordinate system is written by using equation number 3. So by substituting del square in polar coordinate system in equation number 1, then the same equation can be written as minus h cut square divided by 2m. Then the big term, it is related to operator del square, psi r plus v r psi r equal to E psi r. Now that is our equation number 4. Now we come to next slide. Now, considering here that the potential VR is spherically symmetric, that is a central potential, and depends only on the radial coordinate r and independent of angular coordinates theta and phi. So, therefore, equation number 4 is separable in spherical polar coordinates, and we can write in form of equation 5. So psi r can be separated out into radial form and angular form. Radial form is represented as r function r, and angular form is represented as y function theta and phi, and that is separating variables. We remember that in Hamilton-Jacobi equation, when we discuss Hamilton's characteristic function, we separated variables like this only. But there, the separation was time dependent and time independent type of coordinates. Here, it is not time dependent and time independent, but it is depending on the radial distance or the angular part, theta and phi. Now, putting value of psi and separating r and y as per the differentiation. So, using phi in equation number 4. And here the differentiation quantity is d by dr. So r function r is differentiated, not y theta phi. So it is taken out. Again, in the second one, it is del y by del theta. It will be differentiated. R function r is not differentiated, so it is taken out. The last one, again, del 2y by del phi square, it will be differentiated, not r function r. And we do another process also. We divide the whole equation by r, function r, y, theta phi. So that same thing we have done, that every term is divided by r function r by theta phi. Now you will see that here y theta phi in the denominator y theta phi, so it will cancel out. Here r function r in denominator r function r, that will be cancelled out. Again here r function r, and in the denominator r function r, it will be cancelled out. And here we already wrote earlier psi r, again psi r, and again divided by r function r and y theta phi. So that will be cancelled out, and only the remaining part is VR, and that is again ER. And now we come to the next slide. Now, simplifying equation number 6, we can write minus h cut square divided by 2m and 1 upon r square divided by r function r dr, and the differentiation quantity again here 1 upon y theta phi r square sine theta del by del theta sine theta del y by del theta. Again in the last term 1 upon y theta r square sine square theta and del 2y by del phi square Vr is equal to E. Now, rearranging this term and multiplying both the sides by 2r square m. So we multiply both the sides by 2r square m. So again, m is cancelled out and divided by h bar square. So this h bar square is cancelled out. And again, r square is there. So this r square is again cancelled out. So we'll get 1 upon r function r d by dr and r square dr by dr, and it is multiplied by each term. So 2m r square divided by h cut square e minus br, and taking the angular part on the right hand side. Again, we have taken it on the right hand side, and this is taken on the right hand side part. Now, taking this on the right hand side, we'll see that this equation and again this equation both are equal to some constant lambda. So we have equated left hand side equal to right hand side equal to some constant lambda. And on the left hand side, you will see that only r is there. So it is known as a radial part. Here you will not see any theta and phi. And on the right hand side, you will see only theta and phi, not r is found. So it is an angular part, and we call it as equation number 8. And separation is achieved in radial and angular part in equation number 8. Now we come to the next slide. Now focusing on the radial equation only using equation number 8. So here 1 upon r function r, and it is d by dr, r square dr by dr, 2m r square h divided by h cut square e minus vr equal to lambda. That is the radial equation. And we divide both the things by 1 upon r, means multiplying both the things by 1 upon r. So this is again multiplied by 1 upon r. So 1 upon r square. Again here 1 upon r, r square multiplied by 1 upon r square. So it is 2m r square divided by r square and h cut square. I will notice that this r square is cancelled out. So it is equal to 1 upon r square, r function r, d by dr, r square, dr by dr, 2m divided by h cut square, e minus vr is equal to lambda by r square. Because this equation is multiplied throughout by 1 upon r square. Now, this can be rewritten in form of this particular equation. Just we rewrite that equation and we call it equation number 9. Now multiplying both sides by r function r. So again, multiplying both the sides by r function r. So naturally, if we multiply that, this r function r is cancels out with the multiplied r function r in the numerator. So 1 upon r square d by dr. Again here multiplied by 2m r function r divided by h cut square. Again, it is multiplied lambda r function r divided by r square. So multiply both the sides by r function r. Now simplifying that, let us take this term on the left hand side. So we have taken this term on the left-hand side and equated to 0. Now 1 upon r square d by dr, r square dr by dr, plus in bracket, we are taking the r function r common. So 2m divided by h cut square e minus vr minus lambda by r square, r function r is equal to 0. We name it as equation number 10. This equation number 10 contains only r and known as a modified or the radial equation. So earlier equation was still radial equation, but we have further modified the radial equation. Now concentrating on the angular part. So equation number 8, again, one can write the angular equation as follows. So it is the angular part, again, it is equated to lambda. And it is multiplying both the sides by y function theta and phi. So we multiply both the sides by y function theta phi. So here y function theta phi is in denominator. You multiply by y function theta, so it will cancel out. So it is only minus and sine theta del by del theta. The rest of the thing as it is. And here we write that lambda multiplied by y function theta. Then taking this on the one side only, so it is the same equation is equated to 0, and that is equation number 11. So taking all the quantities on the one side and equating it to 0. Now equation number 11 is the angular equation, and it contains only theta and phi. You will not find any r, no radial vector or no radial distance is found. So it is the angular equation only. Now we can further separate equation number 11 into two equations, one for theta, another for phi separately. And for that, we assume that y theta phi s. So y theta phi s equal to theta, capital theta, function small theta, capital phi, function small phi. So that is equation number 12. So now we see that how the further process is done in the next slide. Now, using angular equation, we can write that 1 upon sine theta del by del theta. And now we write y theta phi, again, d2y by d phi square, lambda theta phi. And that is the angular equation, just we repeat it. Now, in place of y theta phi, we are writing theta function theta and y phi function phi. So we have replaced y by theta function theta and phi function phi. Similarly here, del 2 theta function theta, phi function phi by del phi square. Again, lambda is multiplied by this new type of representation. Now we call it as equation number 13, and we do one process multiplying both the sides by sine square theta divided by theta function theta and phi function phi. So we multiply both the sides by this particular thing. So here 1 upon sine theta del by del theta, and this theta function theta phi function phi, and 1 upon sine square d2 phi d2 theta and d phi square. Again we are repeating the same equation. Now we multiply by sine square theta divided by theta function theta and phi function phi. So we multiply that, and we'll notice that one sine theta in the denominator and numerator multiplied by sine square theta. So only one sine theta will remain. And we are dividing by theta function theta and phi function phi. Again, here we'll notice that denominator have is sine theta, sine square theta. And again, multiplication is sine square theta. So sine square theta, sine square theta cancels out. It is 1 upon theta function theta, phi function phi. And the last one is lambda, theta function theta, phi function phi, sine square theta divided by this whole function. You will notice that here that function will cancel out. Theta function theta, phi function phi will cancel out. Again, here it is differentiated related to phi. So theta function theta is not affected, so it can be taken out. So here in the following step, we have taken it out as a not affected part. Here it is a differentiation with respect to d theta function theta by d theta. So phi function phi is not affected, so it is taken out of the differentiation sign. And again, we'll notice that phi function phi is cancels out with the phi function phi in the denominator. So here sine theta divided by theta function theta, and again 1 upon phi function phi, and d2 phi by d phi square, and again lambda plus sine square theta equal to 0. So we call it as equation number 14. Now, equation 14 is having two parts, and just rearranging the equation number 14. So on the left hand side part is having theta only, and the right hand side is having only phi. So it can be separated, and it can be represented as equal to some constant m square. So left hand side equal to right hand side equal to some constant m square. So that is what we have represented in equation number 16. Now equation number 16 minus 1 upon phi function phi d2 phi by d phi square is equal to m square. That we are writing over here, and we are simplifying. So it is d2 phi function phi d phi square plus phi function phi m square is equal to 0. And that is the equation for phi only. And that is equation number 7. Now we have obtained equation just purely for phi. Similarly, just we have to do the process for obtaining equation for theta only. So concentrating on the left hand side part. So sine theta divided by theta function theta, and just repeating the equation number 16, but in terms of equating it to m square. So this is a equation only for theta. Now we do a little more process, multiplying both the sides by theta function theta divided by sine square theta. So we multiply theta function theta divided by sine square theta. So 1 sine theta again cancels out. So in the denominator sine theta, and this theta function theta is cancelled out with theta function theta. So d by d theta, and in the bracket differentiation quantity remains as it is. And here it is again, it is lambda theta function theta and equal to m theta function theta divided by sine square theta. And just we rearrange that, then this quantity, first term as it is, and this quantity, the left hand side part, the right hand side part comes to the left hand side part, and so it is written like that, and both are having function function theta. So we are taking out as a common. So this is equation number 18, and that equation is for theta only. So this equation is obtained only for theta. Now, solution for equation 17, that is for the phi, is written as phi function phi is 1 upon under root 2 e to the power plus or minus I m phi. So equation number 19, m should be positive and phi and its derivatives are needed to be continuous and single valued in the domain 0 less than phi or less than equal to 2 pi. And the factor 1 upon 2 pi raised to 1 half is due to the normalization condition. Now, we are concentrating on equation number 18 and assuming this, it is very important to assume cos theta is equal to omega and theta function theta is equal to p omega. Now, we just try to take a differential. So d omega is equal to minus sine theta d theta. So d omega by d theta is equal to minus sine theta. Now we are taking dp omega by d theta. So it is written as dp omega by d omega by d theta. And we know that dp by d omega as it is, but d omega by d theta is equal to minus sine theta. And again, we have only noticed that p omega is equal to theta function theta. So it is d theta by function theta by d theta. So d by d theta can be written as d omega by d theta, d by d omega is equal to minus sine theta d by d omega. So this is equation number 20. Now, using 18 becomes using 20. So if you use 20 in equation number 18, then it becomes minus sine theta divided by sine theta d by d omega minus sine square theta dp omega by d omega plus lambda minus m square 1 upon 1 minus cos square theta, and p omega is equal to 0. So this becomes sine theta cancels out, minus minus sign becomes plus. So d by d omega 1 minus omega square dp omega by d omega and lambda in another bracket minus m square minus 1 upon omega square, because we have taken cos theta equal to omega and p omega. Now, since theta goes from 0 to pi, the domain of omega is from +1 to -1, because the omega is in terms of cos theta. So that is why the domain changes from +1 to -1. And this is equation number 21, and that can be modified, and one can write in terms of this equation. So one can write this equation and taking the differentiation, because d by d omega is there. If you take a differentiation, it comes into this particular form very simply, just by taking a differentiation. And equation number 24, sorry, 22 is known as a Legendre equation, obtained by taking m is equal to 0. So if you take m equal to 0, only lambda term is remaining, and that is the Legendre differential equation or Legendre equation. It is a very popular equation. Now, for lambda equal to L plus 1, the equation number 21 becomes Legendre equation, and it is known as equation number 22. And PL omega are known as associated Legendre polynomial. For a particular value of L, and M takes only those integral values which satisfy minus L less than equal to M less than equal to +1 plus L. And thus the angular equation 13, we can write the solution. So YLM theta phi, that is known as a spherical harmonics, NLM, it is a normalization constant, PLM cos theta, phi function phi, and this is known as angular term, and equation is 23. Now, now rewriting equation 10 for L equal to L, lambda is equal to L plus 1. So the radial equation is 1 upon r squared d by dr, r squared dr by dr, and in the bracket 2m h cut square e minus vr minus L plus 1 by r square, r function r equal to 0. That is equation number 24. And we are writing lambda equal to L plus 1. Now taking that ur is equal to r function r. So ur is equal to r function r. And one can modify equation number 25. How it is modified? It is shown here that d by dr, r square d by dr, and it is r inverse ur. And if you do the differentiation, it is shown over here. We come to the first differentiation, then second differentiation, and you will notice that here du by dr, here plus du by dr cancels out, and it is r dur by dr square. And the first term is nothing but this first term, nothing but this particular form. And if you put this form and you try to simplify, then you will notice that it is ur is equal to r function r. So each term is multiplied by r function r. It can be replaced by ur. And that equation is replaced in form of this modified radial equation. And that is represented as equation number 25. And how it is modified, that is shown over here. So now we come to another slide. Now we have to apply our the derived equation for any particular problem, so that we can understand that how these equations are used to solve any problem. Now here we are taking a very standard example, and in this standard example, applying radial equation to attractive Coulomb potential. Now, application of radial equation is very important in atom, where the electrons are attracted towards the positively charged nucleus by Coulomb potential. So it is an ideal example of an atom. The nucleus is positively charged, electrons are negatively charged, and they are attracted by Coulomb potential. The potential has a form Vr is equal to minus C by R. And here we are considering C as a positive constant. And in the case of an atom, C is equal to Z E square. where Z is the number of protons in the nucleus and E is the electronic charge. So C can be represented as ZE square. Now using equation 25, putting the potential VR in from equation 26. So we are writing the potential. So using equation number 25, modified radial equation, and we are putting the potential VR is equal to minus C by R, and we'll find that minus minus sign become plus. So the equation is modified that 2m divided by h cut square E plus 2mc divided by R h cut square and minus LL plus 1 divided by R square. Now we modify this equation 27 by assuming that k square is equal to 2m divided by h cut square modulus E, because modulus is taken, E may be positive or E may be negative. Attractive Coulomb potential and bound condition, then E is negative. But if you want to avoid the sign, negative or positive, we write modulus sign so that we don't have to worry about the sign. And again, X is assumed as M into C divided by K H cut square. This is known as equation number 28. Now, we write this equation d2u L R by dr square and minus k square u L R, and that is represented by k square. That 2me is represented by k square. So we have used equation 28, and this term is multiplied and divided by k and minus L plus 1 divided by r square. And again, using equation number 28, we can write d2ulr by dr square minus k square ulr plus 2kx divided by r ulr minus LL plus 1 r square ur equal to 0. Now we name it as equation number 29, and we have to further modify equation number 29. Now rewriting equation number 29, it is d2 by dr square minus k square plus 2kxr divided by r minus LL plus 1 divided by r square ulr, because every term was having ulr, we have taken it out. Now assuming that rho is equal to kr, so naturally r is equal to rho by k, and we can take a differential. So d rho is equal to k dr, and we can write k uh, d by d rho is equal to d by dr, and that is equation number 31. So 30 and 31 are very important. So we are putting these equations into equation number 29. So k square d2 by dr square minus k square again plus 2k square x divided by rho and LL plus 1 k square by rho square UL rho. And we notice that each term was having k square. So k square was taken out and divided. So it is d2 by dr square minus 1 plus 2x divided by rho minus LL plus 1 divided by rho square UL rho equal to 0. So here we have used 30 and 31. And in the last step, we have divided by k square. For the large value of rho, the constant term in the above equation is dominant because rho is in the denominator and in the higher power also. So in this equation, rho is in the denominator. Here, rho square is in the denominator. If rho is very large, then this term becomes small. This term becomes still small. With comparison to constant term, these terms are very small. Therefore, the asymptotic solution is assumed as in the following form. So asymptotic solution means infinitely large distance. It can be assumed that UL rho approximately equal to exponential plus or minus rho. One can try the solution of the form UL rho and to have a proportionality factor GL rho exponential plus or minus rho. And that is equation number 33. The positive sign in equation number 33 is avoided because it will be very large and the value of rho is not admissible. If you take a positive rho, then the probability of finding the value is very large at infinitely large distance, and that is not logical. So it is assumed that we have to take the minus exponential rho. So it is exponential minus rho. So ultimately, we come to the part UL rho is equal to GL rho exponential minus rho instead of plus. And that is equation number 34. Now we take a differentiation DUL rho by D rho. So taking a differentiation first order. Taking a second order differentiation D2UL rho by D rho square. This part is again differentiated. And simplifying D2UL rho by D rho square is equal to e to the power rho minus rho GL rho minus 2 e to the power rho minus rho DGL rho by D rho. And last term is e to the power minus rho D2 GL rho by D rho square. So that is represented by D2 UL rho by D rho square. And using this same thing in equation number, this is equation number 35, and using 35 in 32. So 35 is representing the second order differentiation that is put in equation number 32. And you will notice that each term is having e to the power minus rho. So we divide both the sides by e to the power minus rho. So that term is removed. And we are segregating the differential terms. So it is d2 by d rho square minus 2d by d rho minus 1 plus 1 and plus 2x divided by rho L plus 1 divided by rho square. And that common term we have taken, and the ultimately common term can be divided. So ultimately we can come to the particular part. So plus 1 minus 1 is cancels out, and it is written in form of this particular form. And here, don't focus on this particular equation. There is a spelling mistake and typographical mistake. So correct equation is represented over here by showing the arrow. This arrow shows the correct form because plus 1 and minus 1 is cancels out. So this is equation number 36. Now focusing on equation number 36. Now the solution of equation 36 can be obtained in the standard manner using the power series method. So there is a standard method which is known as a power series method to solve differential equation. So we are using this power series method. So assuming the power series as follows. For that, GL rho is equal to S equal to 0 to infinity AS rho raised to S plus C prime. That is equation 37, which gives C prime as L plus 1. With this, using power series with the value C prime, we get recursion relation for the expansion coefficient AN as follows. So L plus 1, A1 equal to 0. And we get the recursion relation that S plus 1 coefficient divided by AS, that is S minus X in the denominator S plus 1, L plus 1. And this can be represented. And if we take an asymptotic case or tending towards infinity, so if S tending towards infinity, this is very large divided by S very large, again divided by S very large. So one S is cancelled out. So it is ultimately 1 upon S. And that is equation number 38. Now, if X is selected in such a way that power series terminates. So if you take X is equal to S, then automatically the numerator becomes 0 and the power series terminates. And in that case, S is equal to X can be taken as N prime plus L plus 1. Here N is the total quantum number and N prime is a radial quantum number. And in that case, we can still modify as per the following slide. Now, using equation number 28, so we know that k square is equal to 2m divided by h cut square modulus e. And also we know that x is equal to m z e square divided by k h cut square. Now, we know that c is equal to z e square. Now, here we have a value of k. So from this equation, k square, we can put the value of k. So it is z e square divided by h cut and 2m divided by modulus 2e and raised to 1/2, and that is equation number 39. And to remove the under root sign, we take a square on the both sides of equation 39. So squaring equation number 39. So x square is equal to n square equal to z square e raised to 4 divided by h cut square m divided by 2 modulus e. And if you write this equation for E, so take it on the left-hand side, and other part, you take it on the right-hand side. So En, so that is the, for quantum number n, En is equal to minus Ze square divided by 2h cut square n square. Now we have written minus E. The purpose is we have removed the modulus sign. And minus sign, we wrote that it is written for an atom. An electron is bound. For any bound electron, the energy is negative, and that is why the energy eigenvalues are negative. So En is represented as negative. This is a well-known expression for the energy spectrum of hydrogen-like atom. So we have already, in earlier days, we have derived in Bohr atom model this type of equation for hydrogen-like atom. Now, importance of the topic. The three-dimensional case has several applications. This can be used for square well potential, harmonic oscillator, exponential potential, hydrogen-like atom, etc. The atomic orbitals size depends on the radial function. The shape is obtained from the angular function, that is from the spherical harmonics, and energy is obtained from the Schrodinger equation. So this can be solved for one electron system, like hydrogen, like atom, but determined by try and error method for a complex system. So for hydrogen, like atom, it can be solved exactly, but for a complex atom with many electrons, this can be solved by try and error method. Now, for further reading, the quantum mechanics by Wagmare is proposed over here. Now we have to remember the contributors. So Erwin Rudolf Joseph Alexander Schrodinger, very big name. Born in 1887, passed away in 1961. Austrian-Irish physicist and Nobel Prize winner. So his contribution is well known in quantum mechanics by giving the Schrodinger equation. And at the same time, we have to remember the French mathematician Andrea-Marie Legendre, born in 1752, very long back, and passed away in 1833. He was a French mathematician, and his contribution is well known in mathematics, and we use in quantum mechanics Legendre equation, or we try to obtain Legendre equation and use the Legendre equation to solve our quantum mechanics problem. So now we come to another slide, a very interesting slide. Again, I remember Schrodinger, right? Thank you with a pen, having a written Schrodinger, because this is the appropriate way of giving thanks to Schrodinger also and thanking the students also. And these are the beautiful power of a wine white lily, which is grown in my garden in Monson. And thank you very much. Thank you very much for patient hearing. And we just stop our the talk here. Thank you so much.